The next thing which we defined here is a hyperplane. So basically the decision boundary or a hyperplane is the same thing, but when we have in a one-dimensional plane or a two-dimensional plane, we basically call it a decision boundary, which is basically acting as a classifier to classify two different classes. But when we move to a higher dimension from two-dimensional to, for example, three-dimension, then we call it a hyperplane, because it tends to classify the points in more than two dimensions. So you can see here we have two dimension and we have a decision boundary here, but in three-dimensional case, since we were unable to classify these two data points in two dimensional, so normally we transform these data points from two dimensional to three dimension, and in this case the separator is being called as a hyperplane. Then we discussed what a margin is, and we also discussed about what a good margin is and what a bad margin is. So a good margin will be a margin which has the maximum distance for all data points to the hyperplane, but a bad margin is the one which might have not much distance from each data point to the hyperplane. Similarly, we also have the concepts of hard margin and soft margin. In hard margin, we basically separate two sets of data, and we tend to have the distance as large as possible, right? But on the other hand, in soft margin, we may not have this option there. So if you see in this figure, you can see that in hard margin we tend to have a hyperplane having maximum distance for all data points. But if we have somewhat of complex situation in which we have an outlier here, maybe because of noise, then we tend to have a margin which is also able to classify these data points. But in this case, for in a soft margin case, we are basically bearing these misclassifications, right? So why we are bearing these misclassifications? Because our maximum data points are being classified by these margins successfully, but there are few points which are being misclassified. So our accuracy may drop down a little bit, but it will not have a major impact on the overall accuracy of the system. Then we further discussed some mathematical concepts of the support vector machines. So for that mathematical model of support vector machine, I basically give a revision of the basic concepts of linear algebra, in which we saw how can we calculate the magnitude of a vector. Then we saw what a unit vector is and what is the relationship between a unit vector and the magnitude of a vector. And then we also saw how can we calculate the equation of a line, and then how can we calculate equation of hyperplane, and then we saw what is the relationship between these two equations. And then we also saw that how the W transpose of x plus b is equals to 0. Also, we also discussed that the equation for calculating the margin is, right? So by using this example, where we had some positive examples, we have some negative examples, we basically derived this equation in detail in the previous lecture. So if you have still confusion in deriving these equations, please go back to the slides and have a look at the recordings again. And then we also discussed the cost function and the gradient updates mechanism of support vector machine. We also discussed the hinge loss function, and we also had a look at the regularization term. Then after discussing the hinge loss function, we also discussed how can we avoid overfitting in a support vector machine by basically penalizing the vectors or the coefficient of the vectors. So this was the graph which we discussed in detail, and this is the equation which we derived in the last clips of the previous lecture. So this is the point where we stopped in our previous lecture, because up till now we were having a discussion in which we were only discussing the data points which were linear data points, right? And because they were linear in nature, so we were able to classify them even in one-dimensional space or even in two-dimensional space. Now let's go into a little bit of more complex situation in which we have some data points which are not linearly separable or which are non-linear sets of data. For example, here you can see that it is not possible for me to draw a linear line, and I am not able to classify these points through a linear line or a linear decision boundary. So in that case, where we have non-linear data sets, we basically use some kind of tricks, and those tricks are known as kernel tricks in support vector machine. So we basically use different kernel functions within a support vector machine, and those kernel functions help us to classify non-linear data sets. So SVM has a technique which is called as a kernel trick. These are functions which take low dimensional input space and transform it into a higher dimensional space. So the basic objective of a kernel function is to transform a low dimensional data into a higher dimensional data, for example 3 dimension. That is, it converts not separable problem to a separable problem, right? It is mostly useful in non-linear separation problems, the kernel trick. Here is an example in which we have these data points in a one-dimensional space. So you can see we have one dimension here, and we have these two sets of data here. So it is not possible for me to linearly classify these data points because they are in a situation where they form a non-linear problem, right? So now if I convert this one-dimensional space to a two-dimensional space, and then I am able to draw a decision boundary which is able to classify these two sets of data. So what I did is I did transformation of a function which is f of x is equals to x here, because this is one dimension, and I transform this f of x is equals to x into f of x is equals to x raised to the power 2, which means we have now moved from a single dimension to a two dimension. And because of moving or increasing one dimension, we have basically classified these data points. Similarly, if we have the data points in two-dimensional space and we are unable to classify them, then we can move them from two-dimensional to a three-dimensional space. And when we move them from two-dimensional to three-dimensional space, we will have these data points being presented like this way, right? And then we are able to draw a hyperplane which is here, and this hyperplane can basically classify these two sets of data, right? So we have a mapping function which is basically transforming the two-dimensional data into these three dimensions. So SVM kernels. In practice, SVM algorithm is implemented with kernel that transforms an input data space into the required form. So as I explained earlier, that the function of an SVM kernel is to transform a data set to a form so that we can be able to classify them. SVM uses a technique that is called the kernel trick, in which kernel takes a low dimensional input space and transforms that low dimensional input space into a higher dimensional space. In simple words, we can say that kernel converts non-separable problem or non-separable data into the separable problems by adding more dimensions to it. So we can move one dimension to two dimension or two dimension to the three dimension by using these kernel functions. It makes SVM more powerful, flexible, and accurate. So obviously we have much more accuracy and we have much more power in terms of non-linear data sets as well with the help of these kernel functions. So these are the three most commonly used kernel functions which you will see frequently in different support vector machines, and these kernel functions help us to classify non-linear set of data. So you are already familiar with these three functions. I will explain them later in the next slide in detail, but these three kernel functions are Gaussian kernel, so you know that we have this bell-shaped graph for a Gaussian function. Similarly, sigmoidal kernel, we discussed this sigmoid function in great detail in our neural networks lecture, and we saw that how, like in neural networks, we were using this sigmoid function as an activation function there. and here we are using this sigmoidal function, which is the same shape as we discussed before, but now we are using this as a kernel function in SVM. And similarly, we have different polynomial equations of polynomial kernels, which you have already studied in your initial semesters. Same polynomial equations, we use them in SVMs as a kernel functions.